In this video, I'm going to describe how to take the derivative of log functions. So this is what we're after. This is our goal. Our goal is to find if f of x is equal to log base b of x, what is f prime of x? So I'm going to start by doing the following. F of x is equal to log base b of x. Just rewrite the function down that we're interested in. And then say, I don't know how to do this derivative, but can I manipulate the expression to turn it into an expression that I do know how to take the derivative of? And one way to do that is to exponentiate. I'm going to raise both sides as powers on the same base. I'm going to use a base of b, the same base as the log function, so I have access to the cancellation law. So b to the power of f of x is equal to b to the power of log base b of x. I'm going to cancel using the cancellation law. And we have an exponential expression, b to the f of x is equal to x. The next thing I'll do is I'll take the derivative of both sides. And I'll note that b to the f of x is like b to the power of w. W just stands for a function. F of x just stands for a function. When we take the derivative of b to the w, we get b to the w times w prime. When we take the derivative of b to the f, we get b to the f. B to the w times w prime times the ln of b, forgot the ln of b part. When we take the derivative of b to the f, we're going to get b to the f times ln of b times f prime, just with a different letter, just f instead of w. So b to the f of x times the ln of b times w prime. Now, if I'm taking the derivative of the left side, I have to take the derivative of the right side. So the derivative of x, derivative of 1 times x is 1. Now, let's rearrange this. Let's rearrange the expression. Oh, I put a w prime there. I meant to put f prime. My apologies. Force of habit, right? Force of habit. So I'm going to rearrange. I want to get f prime of x all by itself. So I'm going to divide both sides by b to the f of x. I'm going to divide both sides by the ln of b. And I'll get 1 divided by b to the power of f of x times the ln of b. Now we're not quite done, because I'm going to reuse right. We're not quite done. What I'm going to do is I'm going to recycle a part of the expression. I'm going to use it again. The part that said x is the same thing as b to the f of x. So I'm going to replace, since they're equal to each other, I'm going to replace b to the power of f of x with x. I'm going to do that in the bottom line here. So we get 1 over x times the ln of the base. So to summarize what the calculation tells us, we found f prime of x, and f prime of x is what we were after. We were after the derivative of the function f of x, the derivative of log base b of x. So that's now been completed. So a summary is that the derivative d by dx of the function log base b of f of x, or log base b of x, when we're saying log base b of x is equal to 1 over x times the ln of the base. So that's our big conclusion. We could repeat the calculation with ln of x, which is log base e of x, go through all the same manipulations, and get this special case that the derivative d by dx of ln of x is 1 over x times the ln of e. Ln of e is 1, so it's 1 over x times 1, which is just 1 over x. Okay, so that special case is one of the key formulas for derivatives. We treat it as a separate formula very often. Derivative of ln of x is 1 over x. The derivative rule can be combined with the chain rule. If instead of taking the derivative of ln of x, we're taking the derivative of ln of w, we'll get derivative of ln of w is 1 over w multiplied by w prime, which we can simplify by writing w prime divided by w. Oh, and I should have mentioned this in last week's videos, but most substitutions are done using the letter u instead of the letter w. I did mention that you'll see a reason why I use the letter w for this. It's going to be a few weeks when we get to methods of integration and the notation that's used for a method of integration called integration by parts. So it's just a way to avoid any type of confusion with lettering. Anyway, so let's look at an example of taking the derivative of the ln of a function. Derivative of ln of, in this case, x to the power 3 plus 5x to the power 7. So before taking the derivative, I'm going to rewrite the expression. Y is the ln of w with w is equal to x cubed plus 5x to the power 7. We'll take the derivative. W prime is 3x squared plus 35x to the power 6. And we'll need that when we take the derivative of y. Y prime is 1 over w times w prime, which it's fine to go right away to the formula w prime over w. And then I'll fill in the pieces. W prime is 3x squared plus 35x to the power of 6. And then w is x cubed plus 5x to the power of 7. That's a good answer. There's other types of answers that you can have for a question like this. There's different ways you can write the expression, but I think this is the best way to write it. Okay, now we'll also look at combinations of this new log derivative rule with our old derivative rules. For example, the product rule and the quotient rule. On the left-hand side, we have two functions multiplied together. We have a polynomial and a log. To take the derivative, we need a product rule. A is x to the power 5, b is the ln of x. One thing that I noticed when marking, especially the first time someone's working with calculus involving log functions, which probably describes most of the class, is the notation of logs. Because it contains so many letters, you might get confused about what piece belongs where. Ln of x is one thing. It's one function. You cannot separate the ln from the x part. You cannot have the ln of nothing. You have to have the ln of something. Okay, so this is a product rule. When we take the derivative, f prime of x will have a times b prime plus b times a prime. A is x to the power 5. B is ln of x, so b prime, our derivative formula for the derivative of ln of x, is 1 over x. Plus b is ln of x multiplied by the derivative of a, derivative of x to the power 5, which is 5x to the power 4. And it's very tempting for me to simplify this a little bit, so I will. X to the power 5 times 1 over x is the same as x to the power 5 divided by x, just using fraction rules. And then you can use exponent laws. X to the power 5 over x is x to the power 4. Exponent subtract. And the second piece, I'm going to put the polynomial part in front of the log function because that's kind of a standard thing to do. And there's our answer. Yes, you can common factor x to the power 4 out, but this is also okay. Next question involves a quotient rule. This is a t over b, top function over bottom function. So quotient rule. So we saw a chain rule for log functions, a product rule for log functions, and now a quotient rule involving log functions. So our derivative f prime of x will be the bottom function times the derivative of the top minus the top function times the derivative of the bottom divided by the bottom squared. And we'll get the following. The bottom function is x to the power 5. The derivative of the top, derivative of ln of x, is 1 over x, minus the top function, ln of x, times the derivative of the bottom, derivative of x to the power 5 is 5x to the power 4, all divided by the bottom squared, x to the power 5, all squared. I'll simplify a little tiny bit. X to the power 5 times 1 over x is again x to the power 4. And then 5x to the 4 times the ln of x, all divided by, we have a power to a power, the powers are going to multiply, x to the power of 10. So use some exponent laws in there to simplify the expression just a little bit. We can do some common factoring and some canceling, but I think this is a better final answer. Okay, another example. This is a combination rule. And there's actually many ways you can do this. Many formats. I'm going to show you the best way. Whenever you have the ln of a top function over a bottom function, you could say that that whole thing inside the brackets is equal to w. And the derivative of ln of w is 1 over w times w prime, or w prime over w, same thing. You'd have a quotient rule when you calculate w prime, and then you'd have an interesting time dividing that by a fraction and simplifying it. The smartest thing that you can do is the following, is that you can write f of x is equal to the ln of e to the 3x plus 3 minus the ln of x minus 4 times e to the negative x. And how that happened was we used the log property. The log of m over n is equal to the log of m minus the log of n. Now the next thing I'm going to do is I'm going to take the derivative. Actually, I lied. That's not the next thing. The next thing I'm going to do is I'm going to label this and rewrite it. I have the ln of something, I'll call it w, minus, well, I already used w. I could use a different color w if I wanted, but that's kind of weird. If you're making notes, you're hopefully making notes in pencil, and there's only one color of pencil that erases at least. So instead of using a red w or purple w or something, I'm going to use a different letter. I'm going to call it u, ln of u. Now I'll take the derivative of each of those pieces separately. They're separated by a plus sign or minus sign, so the derivatives don't interact with each other. They're two separate derivatives when we differentiate. So f prime of x is going to be w prime over w minus u prime over u. It's the same derivative rule with a different letter. Just w and u each represent functions. W, the function that's represented by that, is e to the 3x plus 3. W prime, we're going to have e to the power of a function times the derivative of that function. So e to the 3x times 3 plus the derivative of the constant is 0. So we just get 3e to the 3x. Then u is equal to x minus 4 times e to the negative x. When we take the derivative of u, derivative of 1 times x is 1. Derivative of negative 4 e to the power of a function, we're going to get negative 4 times e to the function times the derivative of the function. So the derivative of negative x, which is negative 1. And then we can simplify a little bit. We have a negative 4 multiplied by a negative 1. We can multiply those together. So we have a 1 plus 4e to the negative x. And we're just going to throw those into the formula. Throw those into the left-hand side there for w prime and u prime. So w is e to the 3x plus 3. U is x minus 4 e to the negative x. And then throw in the w prime x minus 4 e to the negative. Oh, wrong thing. W prime is 3 e to the 3x. And u prime is 1 plus 4 e to the negative x. And that would be your answer. This is the best answer. Not the only way you can write it, but the best way you can write it. I invite you to compare this to the other method that I mentioned. Treating the whole bracketed expression at the very beginning as w, and then the derivative is w prime over w. Using a quotient rule, you'll get something that looks completely different, but is actually the same. Now at the beginning, we derived the general formula for the derivative of log base b of x, and then we went to the special case ln of x. We'll go back to the general case now, where we found that the derivative of log base b of x is 1 over x times the ln of the base, ln of b. With the chain rule, if we replace x with a w, we just get 1 over w times the ln of b times w prime. We take that derivative, which we can rewrite in a more compact form, w prime over w ln b. So we'll play around with that by looking at some examples. Here we have y is equal to log base 3 of 3 to the x plus 9 to the x, and we're asking for y prime. Before taking the derivative, I'm going to rewrite the expression. Y is equal to log base 3 of w, where w is equal to 3 to the x plus 9 to the x. When we take the derivative, we're going to need w prime, so I'm going to get it right now. W prime is equal to, the derivative of 3 to the x is 3 to the x times the ln of 3. It's an exponential function, so you have to use a special rule for taking derivatives of exponential functions. Derivative of 9 to the x is 9 to the x times the ln of 9. So, same idea. Now, we'll take the derivative, y prime, derivative of log base 3 of w, is w prime over w times the ln of 3. And then we'll substitute it in what we found. W is 3 to the x plus 9 to the x, as given, times the ln of 3. And then on top, we have w prime, which is 3 to the x times the ln of 3 plus 9 to the x times the ln of 9. And that is the answer. Don't do anything weird. Don't do any simplifying. This is the way that it's expected that you'll do the problem. Okay, just like all the other examples, we're now going to combine this derivative rule with our other derivative rules, like the product rule, for example. So we have the derivative of x multiplied by log base 2 of something. This is a product of functions. The first function I'll call a, the second function I'll call b. When we take the derivative, we'll have a times b prime plus b times a prime. A is just equal to 1 times x, and the derivative, a prime, is going to just be 1. B, more interesting, log base 2 of 2 plus x squared. So we have a product rule with a special chain rule, the log chain rule, log base 2 of w. B prime will be w prime over w times the ln of 2, which is going to be 0 plus 2x, derivative of 2 plus x squared, divided by 2 plus x squared times ln 2. And I'll do a light simplification. I'll just drop to 0. Drop the addition of 0 there, so 2x over 2 plus x squared ln 2. Now it is important that there's brackets around the 2 plus x squared. Both terms are multiplied by the ln 2 that came out of that derivative. Okay, so we'll combine all those terms together in our product rule, and we'll leave a giant mess. We won't try to simplify it. So a is x multiplied by the horrible b prime thing we just found, 2x over 2 plus x squared ln 2, plus b, so log base 2 of 2 plus x squared multiplied by 1. And that's our answer. And there, I mean, we could simplify if we wanted. We could say x times 2x is 2x squared. So we'll have 2x squared divided by that stuff. And then hide the multiplication by 1. But, I mean, it's kind of not a dramatic simplification anyway. Second example on the slide is also a product rule. We have a function, exponential function, e to the 7x. I'll call that a. Log base 3 of x, I'll call that b. We again need a product rule. Should write that down. So a question that would come up in class, we were all together in the good old days, together in a classroom learning, you're able to put up your hand and ask questions anytime you want. A question that would come up is, do I have to say I'm using the product rule? And the answer is no, you do not have to. But if asked, you should be able to say so. You should be able to say what rule you're using. So maybe you'll have a list of functions and a list of derivative rules or derivative rule combinations, and maybe you're asked, like on quiz 1, which derivative rules are needed to take the derivative of this function. So you should be able to identify if asked. But if you're not asked, you don't have to say what rules you're using. Anyway, so when we take the derivative, f prime of x, we're going to get a times b prime plus b times a prime. A is e to the 7x. When we take the derivative for a prime, it's not a very good a, we're going to get, that's e to the power of w, so e to the w times w prime, e to the 7x times 7. For b, it's log base 3 of x, and that requires, b prime requires our special derivative rule for log functions, 1 over x times the ln of 3. We'll plug all that data in, those ingredients into our derivative formula, our product rule. So e to the 7x multiplied by b prime, 1 over x ln 3, plus b times a prime, log base 3 of x, multiplied by a prime, which is e to the 7x times 7. And that is a perfectly good answer. You don't have to muck around with it, make it clean or neat or pretty. It would be expected that you'd leave it like this. And the last topic connected to derivatives of log functions is a little bit different. So the name of it sounds like you're just taking the derivative of a log function, but it's more than that. When we take derivatives, our first step is deciding what type of rule to use. So we have to prototype the function, the form of the function, to use the appropriate rule. When we see a variable in the base and a constant power, that tells us we have to use a power rule to take the derivative. If we see a constant base and a variable exponent instead, so if we swap where those ingredients are and put the variable in the exponent instead, that's an exponential function. It requires the exponential derivative rule. If we make them both constants, if the base and the exponent are both constants, what we're going to get is a constant, and the derivative of a constant is 0. But what happens if the base contains the variable and the exponent contains the variable? So the derivative of x to the power of 3 is 3x squared. The derivative of 3 to the x is 3 to the x ln 3. The derivative of 2 to the 3 or 3 to the 3 is 0. What happens if it's x to the power of x? And the answer is on the right hand side of the slide. The derivative of x to the power of x is something weird. It's x to the power of x times 1 plus the ln of x. And what's happening is it's kind of like a power rule, and it's kind of like an exponential derivative rule. It's both. And there's a bit of a product rule feeling to that as well. There are different ways to present how to take the derivative of x to the power of x. I'm not going to go through them. There's a lot of them. I'm going to show you the traditional way, or the most straightforward way in terms of understanding the process. It's messy, but it's mechanical. So the process is as follows. Since we don't have a rule for taking the derivative of a function raised to the power of a function, or a variable raised to the power of a variable, what I'm going to do is I'm going to manipulate the expression to bring it into a form that I have enough rules that I can take the derivative. The manipulation I'm going to use is I'm going to take the log of both sides. You can take log base 10 of both sides if you want, or log base 2 of both sides. The log base that's best to use is the one that creates the least mess. So the cleanest is the natural log. I'm going to ln both sides. So ln y is the ln of x to the power of x. I'm logging both sides. Now on the right hand side, I'm going to use a log property. I'm going to use one of the ones that comes up very often. The log of m to the power of n is n times the log of n. So we have ln y is x times the ln of x. Now we have all the rules we need to take the derivative. On the left-hand side, we have the ln of w, type of an expression, the log of a function. On the right-hand side, we have a product rule. So this is our a, this is our b. Ln y is like ln w. So what we'll do is we'll take the derivative of both sides, d by dx of both sides. So on the left-hand side, we have the derivative of ln y. The derivative of ln w is w prime over w. Derivative of ln y is y prime over y. Just the chain rule. And then on the right-hand side, we have the product rule, ab prime plus ba prime. So y prime over y is equal to a, which is x, times b prime, the derivative of ln of x is 1 over x, plus b, ln of x, multiplied by the derivative of x, which is 1. We can simplify. X times 1 over x is 1. Ln of x times 1 is just ln of x. So we get y prime over y is equal to 1 plus the ln of x. Now this isn't what we were asked for. We were asked for y prime. We currently have y prime divided by y. So I'm going to cross multiply and get y prime all by itself. So y prime is equal to y multiplied by both of those terms. Add it together, 1 plus ln of x. And this isn't quite what we want either. Our original function y was only in terms of x, and now our answer contains x and y. But it's easy to fix this. At the very beginning, it tells us what y is equal to. It tells us that y is equal to x to the power of x. So I'm just going to replace it. So y is equal to x to the x. So y prime is x to the x times 1 plus ln of x. It's not very nice, but it's mechanical. The only thinking piece that you have to do is at the very beginning. You have to realize that anytime you have a function raised to the power of a function, or anytime the variable appears in the base and the exponent, that you have to use this special rule, this logarithmic differentiation process. Here's another type of example that's very similar. I'll start by taking the ln of both sides. Ln y is equal to the ln of 2x plus 1 to the power of 3x plus 2. we'll bring the power down. So I'll bring the 3x plus 2 down in front. I'm going to make sure that the entire thing multiplies by the log of that function, ln of 2x plus 1. Next, we'll take the derivative of both sides with respect to x. So we have something that's like a ln of w on the left-hand side, and we have a product rule on the right. In general, you'll have a product rule at this stage, or no matter what. If you're using logarithmic differentiation, you're going to have y prime over y equals product rule. So we take the derivative, and we get y prime over y is equal to ab prime plus ba prime. So y prime over y is equal to a, 3x plus 2, times b prime. B is the ln of 2x plus 1, so I'll have ln of w, derivative of ln w, w prime over w. Derivative of 2x plus 1 is 2, so 2 over 2x plus 1, plus b, ln of 2x plus 1, times the derivative of 3x plus 2, which is 3. I'll label those pieces there. So the 2 over 2x plus 1, that was w prime over w, and the 3 was the derivative of 3x plus 2. Okay. Getting close to having this one wrapped up. I'm going to cross multiply by y. So y prime is equal to y multiplied by all this stuff. I'm going to clean up a little bit. I have 3x plus 2 multiplied by the 2. So 6x plus 4 over 2x plus 1. I'll put the 3 out front of the log function, 3 times the ln of 2x plus 1. So a little bit of simplifying there. And then last step, I replace the y by what it is originally, 2x plus 1 to the power of 3x plus 2 times all that mess that is in the box, in the square brackets there. That'll be our answer, unless I mess something up. So yeah, it's yucky, it's messy, it's harder than any type of other derivative rule, but it's mechanical. You don't, the only thinking step, the only real thinking step is at the very beginning, recognizing that you have x appearing in the base and x appearing in the exponent, and you got to do this weird thing to take the derivative. Okay, last example in this video on log derivatives. Nasty looking, horrible function. Most important thing is recognizing that in order to take the derivative of this horrible looking function, you need logarithmic differentiation. Now before doing that, I'm going to rewrite the function. I'm going to rewrite it so it's a little bit neater. It's x to the power of -1 instead of 1 over x, just using exponent notation, plus x to the power of -x. Now I'll take the ln of both sides. So ln y is equal to the ln of all that stuff, x to the power of -1 plus x, all to the power of x. We'll bring the x down using that log property. X times the ln of x to the power of -1 plus x. And now we'll take the derivative of both sides. On the right hand side, we again, oh, I messed something up. So no one was in class to yell at me. Where did the negative sign go? It didn't go anywhere. It's still there, I just forgot it. Okay, so the negative is still there, it didn't disappear. It came down when we use that log property. Log of m to the n is n times log of n. N times log of n. We have a product rule. Now we have two functions multiplied together. We have an a and a b. A is -x, b is the log of that stuff. Derivative of negative 1 times x is negative 1. B is the ln of x to the power of negative 1 plus x. B prime is w prime over w, calling everything inside the log function w. Derivative of x to the power of negative 1 is negative x to the negative 2. Using the power rule, derivative of 1 times x is just 1. All divided by x to the power of negative 1 plus x. Okay, we'll substitute all that in. It's going to be messy, but that's okay. Doesn't have to be nice. Ln y is equal to ab prime plus ba prime. Oh, not ln y prime over y. So we took the derivative of both sides. So y prime over y is equal to negative x multiplied by b prime, negative x to negative 2 plus 1 over x to negative 1 plus x, plus b, the ln of x to negative 1 plus x multiplied by negative 1. And then we'll cross multiply. Y prime is equal to y multiplied by all that stuff. So I'll have negative x times, you can simplify if you want. I'll leave it messy. Maybe change that to a minus sign. Multiply by the negative 1, put the negative up front. Very, very minor simplification. And then our only step that remains is to replace the y with what it is originally. So 1 over x plus x to the negative x times all that stuff. Negative x times negative x to the power of negative 2 plus 1 divided by x to the power of negative 1 plus x minus the ln of x to the power of negative 1 plus x. So don't do anything fancy. Don't try to be a hero. Simplify and do common denominator, bizarro stuff. Let's leave it like that. Okay, and that's the end of this video.